What's up and hello to you all mindsetters, you awesome grade 11s, and today officially I as Abram call you pre-matriculants. Welcome to Learn Extra Live. It is physical sciences for grade 11s. Well, let's enjoy because we're here to learn more and learn extra. I'm joined by Mr. Tinyiko. Se, kunjan?
Nifukile unjani buthi?
Nami nampukile. Hi, anamaka man.
Yeah, I saw akufanele kuba na trouble ni. And
Yeah.
like you have already said, actually during our time we used to call grade 11s metric 1. You know, that's metric 1. So you're going to have your metric 2 next year.
I like that for
Yeah.
metric 1. What are we
Yeah.
having in store?
Well, today we're going to treat a section that is very important and it has been brought back into the syllabus, and I can tell you it is demanding, but it's very interesting to learn about. We are going to talk about forces basically, so we'll be investigating forces today. And to be more specific, we will be looking at a quick revision of what you did in grade 10, where we're talking about this concept of vectors and looking at what substances actual, what are these physical things that we can classify as vectors. We will also be looking at scalars, but our main focus is about these vectors because in physics we work with vectors in most of the times. So that's what we will be doing. We'll also be showing you how to draw free body diagrams, of course looking at forces acting on objects. We'll also use trigonometry, okay, to find the resultant of two perpendicular forces. So there will be some good measure of mathematics there. So please concentrate, learn with us, make sure you understand each and everything that we're going to do, especially when we begin to dissect these forces and label them and explain them, how to find resultants and all those other things. Yeah.
Ile kujonzeni kati forces.
I saw.
I saw. Well,
Yeah.
Swiss, let me tell you, mindset, why do you need to get in touch with us? Go to Facebook, like our page. It is facebook.com/learnextra. Invite all your friends to like the page too, because we are a community that wants to help each other and to share information. That's why we're calling ourselves a mindset tribe. Otherwise, you can follow us on Twitter @learnextra. And lastly, download your notes from our website, which is learn.mindset.co.za. First link notes are posted on our website, on our Facebook page, but also we have a challenge question for you today. So make sure that you get all the information on our Facebook page. Tell us more about it, by the way.
Basically, let me just highlight to them quickly, Abram, the challenge question that we have, and I'm going to try and give you some input there in terms of trying to give you pointers and clues to how to deal with this question. The question says, a box rests on a smooth, frictionless surface, and Trevor exerts a force or a horizontal force. Now this is key. Horizontal force of 12 newtons on a box, on the box, and on a bearing. Now you need to know what a bearing is. On a bearing of 35 degrees. Okay. Now that is direction. Bearing is direction. This is direction measured from the north as your reference point, okay? So you measure that, making use of your protractor, of course. So please make sure that as we go on in this lesson, scrap around into your books, in your bag and instrument, mathematical instruments, and you come out with that protractor so that we can use it here. At the same time, we find that Tulani exerts a horizontal force as well of 5 newtons on a bearing of 305 degrees. Calculate the resultant horizontal force acting on the box. Now understand here that we're talking about A or both these forces acting on a horizontal plane. So we're talking about measuring the direction from the north, being the bearing. So what it means is that you need to identify your north, all right? And remember that everything is on this plane. So there is the north, one force acting on a particular bearing. So they said 305, I believe it will be somewhere here. Then from there, they say 35, it will be somewhere there. So try and sketch that. Because when you sketch it, it becomes easier to work from that sketch. Of course, solution to this problem would have to be geometrical, okay? So some geometry is going to be applied here for you to be able to find the solution. So please make sure you come up with that sketch, all right? And then That will be the question. You find the resultant. And in the lesson, we'll be explaining thoroughly what those things are. Let's move on now. Let's get deep into this section here where we're talking about these vectors. And of course, force is a vector quantity, and we will be explaining more as we move on. But a vector is this mathematical tool we use in physics when quantities have size, so here they've got how big they are, and apart from that, they've got direction, so we know in which direction these quantities are actually moving. And of course, they also have specific SI unit. What does SI stand for? Some of you are already answering it. It's System International Unit. So this is the kind of unit that is used everywhere in the globe. If you are in South Africa, you're talking distance, you're talking meters, you're talking displacement, you know we're talking about meters as the measuring unit. Whether you are in London, whether you're in Nevada, wherever you are in the globe, you should be using that particular SI unit. Okay, so quantities that have size and specific SI unit only, those will be called scalar quantities. Okay, let me give you an example. For example, when we talk of time, I know that this lesson is to last an hour. So that is the time. So 60 minutes. And then in terms of seconds, because that is the SI unit of time, we're talking about 3,600 seconds. All right? So 3,600 seconds, we only have how big the quantity is, 3,600. And the unit of measurement, seconds only. And that is a it's a scalar quantity. With a vector quantity, we have direction, as we're going to see in the following examples. Let's just come down to this point here. Okay. Now, if we talk of displacement, this is the change in position of an object, and the SI unit in which we measure it is what we call meters. All right? So change in position of an object. I am an object. I am here now. All right? So I can change position in that direction. Okay? Hope you can still find me here. Now, I have changed direction. All right? Now, that is displacement. And therefore, displacement has got how far did I move and in which direction. Both are there. And I can also measure this quantity in some SI unit, in this case, meters. And therefore, displacement is a vector quantity. Velocity, on the other hand, we define it as the rate of change in position of an object. And the SI unit for that is what we call meters per second. Okay? Now, rate, I need to quickly remind you of this now. Once we talk rate, we're talking about something changing over time. So if we say velocity is rate of change of position, okay, in position, it means you have got velocity equals change in your displacement there, okay, which would be, so that is change in displacement over change in time. So we've got time there as the dividing factor. And hence the unit of measurement is meters per second. All right? Moving on. Another example of a vector quantity is acceleration. Acceleration is the rate of change of velocity of an object. And the SI unit is meters per square second. Now, remember I said when we talk of rate, you're dividing by time. So acceleration, therefore, okay, would be A. It will be A for acceleration, given by change in velocity, okay, divided by the change in time, because the rate of change of velocity means you are dividing by time. You're dividing velocity by time. So that's what is happening. Now get these things simple and straightforward. Rate of change of position, it's velocity, delta x over delta t. Rate of change of acceleration, delta v over delta t. Rate of change of velocity is acceleration. Okay. Now, like I said earlier on, we're doing all this because we want to talk about forces, and a force is a vector quantity. So force is one of the examples of vector quantities. We define it, let's give it a grade 7, grade 8 definition, all right? It's a push or a pull exerted on an object. And the SI unit of measurement for force, it's what we call newtons, and the symbol for it is capital letter N. Now, I need to pause here and tell you that please stick to the notation of symbols and everything in science. If you come and put small letter n as a unit of force, say you say 10 newtons, you write it like that, that's incorrect, because small letter n means something else in physics or in physical sciences. Therefore, you have to stick to the given notations. Remember, we're talking about system international units here. All right, so in that way, this will be wrong and that will be correct. Okay, that's the way it is. Okay, now moving on, we can represent vectors by means of drawings, and we draw an arrow to represent a vector. It could be any vector. If it's a force, it will represent a force. If it's a velocity, it will be that velocity. Now here, for example, we have this arrow here. If this arrow is used to represent a vector, the length of the arrow from the tail, this is the tail, the point here, the beginning point, the tail, to the head, all that part represents what we call the size or the magnitude of the vector, how big that vector is. And the arrow, okay, and this arrow there, so this arm here up to that point is the size, but this arrow here represents the direction. Remember that a vector has got both magnitude and direction, and of course it is measured in a specific system international unit. Okay, now, so that is what it means. Now, the length of the arrow, like I've explained, from tail to head, you need to know these things as well. Tail to head. You used to think, what does a vector has a tail and a head? Now, a vector has a tail and a head. The tail is the starting point. The head is where is the end part where the arrow is. Sometimes you might find that a vector is represented like that and the arrow is written in the middle. There's nothing wrong about it. Still, that length there, it's your magnitude, and the arrow, it's your direction. That's all. Okay, and this will be the tail, where it starts, and where it is heading at the end, that will be the head. So if we talk of the tail to head method, which is something we will touch on as we move on now, you should be able to see where that tail to head comes from. Okay, so this is what we have here. All right. There are different types of showing directions, okay? E.g., we can say something is going up or down, or we can say something is going to the left or to the right. All these are directions. Or we can make use of compass points, e.g., the north, the east, the west, the south, okay, as you know, the cardinal points. All right. But then another way of showing direction is by angles. And here you can say 45 degrees to the horizontal, or you can also talk about bearings, where you make use of the angle measured from the north as your direction. Okay. Now look at this here, adding vectors together. All right. Quickly, and I'll come back to this also afterwards. The sum of two or more vectors is called a resultant. And when we have two or more vectors, like here, I've got this vector and that vector, I have placed them tail to head. So you can see there is the head of the first one and there is the tail of the second one. They are placed tail to head. And if I draw a line from the tail of the first one to the head of the second one, this here is called the resultant. Okay? The sum of two or more vectors is called a resultant. And here we used the tail to head method. All right, so let's continue with this lesson when we come back.
Well said, sir. And a big shout out to the mindsetters that are watching, especially to Daniel and also Gift and Chaps, the mindsetters that have passed so well last year from grade 10. You are now on Matric 1. Well done, mindsetters. Otherwise, the challenge question is posted on the page. So get on it and test yourself. And let's see you after the break. Welcome back, pre-matriculants. If you're joining us now, you're a bit late, but you can still catch up because you're on the right time because it is question time. If you haven't done the challenge question, make sure that you go to facebook.com/learnextra, like our page, and also comment on the post that is there on the challenge question. Otherwise, you can also send us your questions. If you're struggling somewhere, we're here to help you through. Mr. Tinyiko is here to help you too. So,
definitely, yes. And we are moving on with the lesson, and this time we're coming into question time, and we're going to see how you will be facing those exam type questions and how you are expected to answer them. So let's just have a look at this one here. It is, when you download these notes, you will see there's this section here that says improve your skills, and these are questions that you need to try and work on time and again. Even when long after the lesson, try and practice on them and see if you can do them. Let's look at this one here. Question 1. Xoli exerts a force of 8 newtons. So we've got 8 Newton force here exerted by Xoli on the box, placed on a horizontal frictionless surface. At the same time, Pretty exerts a horizontal force of 10 newtons at an angle of 90 degrees to the force that Xoli is applying. Then calculate the magnitude, see now, magnitude and direction of the resultant of these two forces. So we need to get a resultant of the two forces. Remember, for us to get the resultant of two forces acting together, we need to put them tail to head, and then we find that resultant. And let me just do this quickly, because a sketch is always very handy to help us answer questions in physics. So you have, say you have that force there. Oh, okay. Now let me just use this one now. Say I've got this force here. Okay. There is the force. And that is the force that Xoli is applying. And I have another force here. So let me use a different color. I have another force there applied by the other person. You can see that I'm trying to use, let's just go back to the question. You see 10 newtons and 10 newtons by Pretty and 8 newtons by Xoli. So they are not of the same length, okay, like that. All right, so we come back here now. We say this is your 8 newtons by Xoli and 10 newtons by Pretty. But these are vector quantities, so what I need to do is to make sure that I actually put direction to them. So that is the direction of the first one. It's upwards, and the direction of the second one, it's that way. But all these are actually on the plane like that. So you've got one going like that and the other one going like that. That's why we're talking horizontal, okay, in that way. So if I have them like this, I can therefore place them tail to head, the first thing that I need to do. Or if I don't place them tail to head, I can use the parallelogram method. But let me just place them tail to head, all right? So I can do this here. Okay, let me let me just move this one. Say I move the white one to this point here. Okay. Sorry. So I've got the white one. Where's the white one? Okay. Let me just use this color here. So let me draw it there. Okay, there we go. So it's this one here now that Xoli is exiting. All right. And it is there, and it is in that direction. So I have it in that direction there. Okay. So I have moved this force here to that point so that I've got tail to head. Okay. So I've used that method as well. Now the line that is from here, from that point to that point there, that line, okay? Okay. So that line there, okay? This line here will be my resultant. And that is again a vector quantity. So what I'm going to have there is an arrow showing direction. So this is the resultant force. Because I'm talking about forces here, this will be the resultant force between the two. And the question wants me to calculate for the magnitude and the direction. Now the direction will be that angle there, all right? And the magnitude, if you look at this, if I've got a 90-degree angle there, it means I can use the Pythagoras theorem to calculate for this. So what will I do? I'll say that resultant squared will be equal to the square of the force by Xoli, all right, square of the force by Xoli. All right, so this is force by Xoli squared plus the force by Pretty squared. So that will be equal to, that, let's have a look at it. This is 8 squared plus this one by Pretty, it's 10 squared. So you've got 8 squared, it's 64, plus 10 squared is 100, so you've got 164. So your resultant force is the square root of 164 that you can calculate. And let's quickly get calculator here. It's fine. What will be the square root of 164? Let me look for my calculator. I don't have it now, but that will be the magnitude, okay, of the resultant of the two forces. It will be the square root of 164. You can actually work it out there and perhaps also send it through. Abraham will be able to get it to us. Now, quickly, you look at this one. You are to also find the direction, because this is the magnitude, if you like. So all what you've done here is to get the magnitude, or what we call the size. Okay, so what is left is for us to get the direction, and to get the direction we need to make use of trig ratios. Some geometry here is involved. And what trig ratio can we use? Because if you check here, this part here, this one here, it's 8 Newton. This is the force exerted by Xoli. It's this force here, all right? And this one, if we look at the relationship between the two and the angle, you will see that this one is opposite the angle theta, and this one is adjacent to the angle theta. Now, a trig ratio that gives us a relationship between the opposite and the adjacent sides is what we call the tangent. Okay, so the tangent of the angle theta is given by what? It's given by 8, which is opposite, over adjacent, which is 10, and that will be 0,8. Now 0,8 We want the angle theta. Now, theta will be the tan inverse. So using your calculator, tan inverse of 0,8, which is 38,66. All right? So 38,66 degrees, it's the angle there that we're talking about here. Now, at the end, giving the total solution to this, it would mean that your resultant R, the resultant force R, in fact, you can even say F subscript R to say resultant force will be given by square root of 164 at at an angle of what? Of 38.66 degrees. Okay, so there you have answered the question in full. You have shown everything. It was about magnitude and direction. Okay, so that's what you have. So you can see that that angle there is what we're talking about. That is the 38.66 degrees. Okay, good. Now, moving on to the next one. Look at this question here. Question number 2. A large metal sphere with a mass of 500 kilograms is suspended by cables on a construction site as shown in the sketch below. So that's cable B, all right? And then you've got cable A there. So don't forget that the mass is 500 kilograms. So this is the mass of the sphere. Now from here you can tell that the gravitational force on the sphere, which is always given by mass times gravitational acceleration, will be 500 times 9.8. And that works out to 4,900 newtons. Okay? So that will be the force there. Now, draw a free body diagram to show all the forces acting on the metal sphere. Now, a free body diagram, when it's a free body diagram, you need to use a dot to represent that body. Even if it's a ball or a box or a car or anything, don't go and waste time and try to draw that car. When they say free body, it means remove the body and use a dot to represent it. So we're going to use a dot to represent the what? To represent that sphere. And then showing the forces acting on it. You know there is this force there. All right? There is the weight or the gravitational force on that sphere, and there is the tension in that cable there. So that's what you have in here. So if you were to label them, you can see this is cable B, that is cable A. So you can say that this is force due to cable B, and this is force due to cable A. And therefore, this one obviously is the weight, or what we call the gravitational force on that. Then B says, draw a sketch to show the resultant of the forces acting on the sphere while the sphere is suspended. Now, when it is still suspended there, both cable A and cable B are there acting on the object. What we can't see is, of course, the gravitational force, but it is there and acting there. So if we are to draw a sketch to show the resultant of all those forces acting on the object, you can, for example, say, okay, let me start with the horizontal force. Remember, this one is acting in that direction, okay? And I need to have these forces now in a tail-to-head situation, okay? So if I have this one there, and I have, you see the head of this force of the cable B. This is force of cable B. I want to put in the weight. I don't want to put it there because I'm now showing the forces such that I can have the resultant. So I must put them tail to head. Then I put this one there. This is the weight. This is FG. All right? And obviously, this one here, oh, okay, obviously the force from there down here, all right, tried my best to get it there. This will be the force due to cable A, and of course what has been erased here, force due to gravity. So that is the direction of the force due to gravity. That's the direction of the force due to cable A. And if you see here, you've got a closed diagram. Now, with a closed diagram, when you're dealing with vectors, that tells you that the resultant is 0. The resultant force is 0 newtons on this set of forces here, okay? Now, if cable A breaks, so cable A breaks, this one here goes away, all right? So let's say this one goes away, all right? Calculate the resultant force. Now, the resultant force when cable A breaks, obviously it will be a force along cable A, but in the opposite direction because it must replace that. So if we were to find that, if we were to find this, this force here, all right, we would say that the resultant force, let me put it that way, resultant force will be equal to the tension on cable A, but in opposite direction. Okay, in opposite direction. Okay, so that's what is going to happen, and we can basically calculate for it, but I want to rush to this last one here where we have to calculate, and so you can see most of the things here. The tension in cable B is 2,500 newtons at the moment. Cable A breaks. Calculate the magnitude of the resultant force. Now, what it means here is that here you've got 2,500 newtons, and here we know that we've got 4,900 newtons. Okay, and if we want to get how much that resistance is resultant is going to be, we have got a right-angled triangle, so we can make use of the theorem of Pythagoras. Okay, so the resultant force squared will be equal to 4,900 squared plus 4,900 squared plus 2,500. Ooh, 2,500 squared. Okay, and then you work that out. Don't have much time now. So here you just are interested only in the magnitude. So from here you can work it out and actually get what the magnitude is going to be without showing the direction. And this is how the questions are going to be like. Some questions will say, just give us the magnitude. Find out how much this thing is going to be, how big it's going to be, what will be the size. Not necessarily showing the direction like we did in the earlier ones where you calculate for the angle. All right, yes. Now, so if you work this one out, it's going to give you 302.6, and so you have got that huge number here. You're going to have it as 30,260,000 newtons. Okay, and of course you can write this in scientific notation and say this is 3.03 by 10 to the power 1, 2, 1, 2, 3, 4, 5, 6. Okay, newtons. Sorry about that, and this thing moved off. So that will be the answer that you're going to get. Let's meet again after this short break.
Intiso se fanele ye mavengeleni.
Yeah.
But I'm enjoying the vibes on the Facebook page and the feedback from the mindsetters, such as Witness Rurunwa, all the way from Zimbabwe, saying, mindsetters, I'm also enjoying the lesson. It's the best. Gift saying, this lesson just gets more interesting. Let's wait and see what's going to happen. Otherwise,
Okay.
keep it tuned in on 319. We'll see you after the break. Welcome back, Mindsetters. Now, on the Facebook page, we've been getting a lot of answers on the challenge question. Sir, are you
Yeah.
ready to give us the right answer?
Yes, I'm ready. Let's just go through it and let's see who got it right and who didn't get it right. And it's very interesting that people are sitting on different ends of the country, and then you can't be checking on each other's answers. Let's just go through it now. It says, a box rests on a smooth or frictionless surface. Trevor exerts a horizontal force of 12 newtons on a box or on the box at a bearing of 35 degrees. At the same time, Tulani exerts a horizontal force of 5 newtons on a bearing of 305 degrees. Calculate the resultant horizontal force acting on the box. So we're talking about this thing happening here on the plate, horizontal, one force in that angle, another one in that angle. So we want to find the resultant force acting on the box. Now I put in here cardinal points because this talks, the direction is given to us in terms of bearing. Now if direction is given to us in terms of bearing, every angle is measured from the north. So if you go back to the question says, the first guy here, all right, 12 Newton on the box, bearing of 35 degrees. That is the force that is exerted by Trevor there. So 35 degrees means on the north, you're measuring 35. Clockwise, of course, not anti-clockwise, clockwise. So you take your protractor, okay, your protractor, you place it in there, you look for 35 degrees, maybe you find it to be somewhere at that point, and then you will put down your ruler and draw a line from there, passing through that. Don't know what's going on with my lines today. Let me try and do this now. Okay, so let me use this color here. So say that is the 12 newtons, okay? So 12 newtons in that direction, okay? I'll put the arrows later on. And then for Tulani, you see, this is going to be 300 and, okay, let me just show you now quickly. If this is to be 35 degrees, so it means that angle there is 35. Okay, that's a bearing of 35 degrees. But then Tulani exerts it at an angle of 305. 305, it's going to be something, you're going to come here, 90, 180, 270, 305 somewhere there, somewhere at that point. Okay, so if I am to draw the force that Tulani is exerting, say it is that force here, and this is only 5 newtons, and therefore it should be somewhere there. They mustn't be of the same, okay, right. There we go. So now we have this now, this part here, from there to there. That is a bearing of 305 degrees, okay? And remember, we're talking about vectors, so this has an arrow in that direction, and this one here has an arrow in that direction. So that's what we are having. Now, if there's something that I want you to check here, if you look at 305 to here, to get to 360, you have got 55. Okay, you need 55 degrees to get to 60 there. Now 55 degrees and the 35 this side, what do they give you? They give you 90 degrees. So that works out to 90 degrees. In other words, the angle there between the two forces is 90 degrees, such that if I work out the resultant here, I can actually make use of the theorem of Pythagoras to work out my solution. So I can say that the resultant here is going to be, I can then arrange them tail to head and work it out. It's going to be 5 newtons. So that squared, 5 newtons squared for Trevor plus, what's the other one? Let's be sure. The other one is 12. So 12 Newton squared for Trevor. Now 5 squared is 25. 12 squared is 144. What will that be? Let's work it out. We have a calculator here now. So we're going to have 25. Okay. Oh, come on. 25 plus 144. 144. That's what we have. So 169. So we'll be having a square root of 169. So we're going to go for the square root of 169. And what will that be? That will be 13. Okay. So that means that the F resultant, the resultant force, is going to be 13 newtons. Okay? Now 13 newtons, we're not done. We need to find the angle. And for us to do that, you can quickly put this into a small diagram. Okay? That's what you have. You arrange these two forces in tail to head. You will see that you have got this one here. All right? So let me put it here where I have got space. Okay? So you would have that. And therefore, the resultant will be this one here, the one from the tail to the head of the other. So that will be your FR, where your 90-degree angle is there. And remember that it's your 5, and this is your 12. So once you are here, you can then say, to get the direction, let the tangent of that angle there be opposite of our hypotenuse. Okay, so opposite the angle is this one here. That is the angle we're talking about. So the opposite side is that, and the adjacent side is this one here. So it will be 5 over 12, and that will be 0, comma. So let's work it out, making use of a calculator here. So we've got 5. Okay, we've got 5 divided by 12. Right, so we have that as 0.417. 0.417. You can actually make it 0.42. So the tan inverse of that will give us the theta. So we will say that this is, therefore, we want to get the tan inverse of that. Oh, so we have the tan inverse. Okay, so we're gonna go shift tan inverse of 0.42. 0.442. All right, and what do we get? We get it to be the tan inverse of 0.2. Something went wrong here. Let's go back. Okay, come back to the calculator. Okay, so tan inverse, shift tan inverse 0.42. for 2. And the answer is 22.78 degrees. So the angle there is 22.78 degrees. 22.78 degrees. Now, for you to finally say I've calculated and found the answer, you would say that, because remember that resultant is going in some direction there. All right, sorry about that. Let me undo whatever I did there. Okay, so that angle is somewhere here, all right. So that would mean that it is making an angle of 22.78 degrees with what? With this angle here, with this arm here, with this force here, which is the 12 degree angle. It is this angle here. Now, if that is your direction, if that is your direction, you can actually give it in terms of bearing if you want to, all right? You can give it in terms of bearing because your north will still be there. Obviously, it will be your 35 degrees less the 22, okay? Less the 22.78, and then you get your bearing. But it is suffice actually to give it like that. You can say at an angle here of 22.78, and like I said, you can give it in degrees in a bearing where you say, okay, it is this angle here minus that 22.78 minus 30 is it 35. Let me just do that. Gives us minus 12. So it's actually at a bearing of 12.23 degrees. Okay. So at a bearing, or you can say this is at a bearing, if you don't want to put it that way. All right? You can say this is at a bearing of 12.23 degrees. You can work it out up to that point. Now, how many people got that right?
So many people.
So many people got it right. Oh, that's great. Abraham is saying so many people got it right. Congratulations, you did so well. And for the other questions, quickly, let's see how many we can answer.
Let's take this one from Salanati. Is it not important to write 0 before the degrees representing direction if degrees are less than 100 so that we can clearly know that it is the bearing? For example, 0.45 degrees.
Okay, you can do that. I understand what you're saying, because when we're talking about bearing, we're talking about that, okay, a revolution will be 360. So you've got 3 digits actually. So you can do that just for you to help yourself understand what's happening. But don't expect it to be in the question papers, national question papers and stuff, because with that, they will always say at a bearing of. So they expect you to know that we're talking about measuring direction from the north. But then a good one for you, use it. I think it's helpful for you to remember when you have that 0.
All right. Here's another one from Xolani. How is Newton related to mass and acceleration?
Okay, quickly. From a mass of an object, we can get the weight, the gravitational force acting on that object, which is a force in newtons. Like we did with a sphere there that was hanging. We calculated for the gravitational force, mass times gravity. I mean, so then we get that. So that's how mass is related. Or related to acceleration, of course, remember, G is acceleration due to gravity. And even when we're talking about the resultant force acting on an object, not necessarily the gravitational force. We have that formula there that relates mass to acceleration. So that's how we find the newtons related to mass, related to acceleration. Okay.
Well, that's where we ended today.
That's where we come to an end, and thank you so much for watching.
Thank you so much, Mindsetters, and always remember that your mind is the most powerful thing ever. If it's filled with positive stuff, trust me, only great things will come out of it. So never give up, because we're here as Mindset to help you throughout. Premature Lines, we believe in you. But from us, today we just want to call it a wrap and say peace.